Assalamu alaikum, dear student. Again, Mr. Gr12 with you. We continue part number 4 of lesson 3.2, photoelectric emission of electrons. In this part, we will cover the following objectives as shown in front of you. Let me read them together. To define the stopping potential and use the concept of loss of kinetic energy equals the gain of electric potential energy using the equation of half mv square equal ev stopping, and we will explain the details of this. Then we will study the graph of stopping potential versus the frequency or the wavelength. Okay, so we start our work with defining stopping potential. As we see in front of us, the stopping potential is the minimum value of potential difference or the minimum value of voltage necessary or needed to stop the electron which is emitted from the electrode. To start explaining that, let me remember what we did before. The figure, this figure, what we observed down. Let me change the color. Okay. If you remember before, we were lighting using, we directing photons or light toward the negative electrode. It's the side which is rich with electron. Okay. And the electrons, they were emitting maximum kinetic energy. Actually, they have range of kinetic energy, but here the emitted electrons, some of them moving with maximum kinetic energy. So what's changed now? Now what we need to do, we will reverse the poles of the voltage. Here we see the negative side of the negative pole of the source is connected to the electrode, the cathode, because it's negative here. You see, it's negative because it's connected to negative. So what I will do now to study stopping potential, I will reverse this voltage in order to light on anode instead of cathode, like what you will observe now. So when we reverse the voltage of the battery, what happens? We will have this condition. So now, as you see in our experiment, instead of lighting on cathode, we are lighting on the positive electrode or the anode. But still we have electrons here, you see. So when you light on anode, of course, still there's some electrons, so they will leave the surface with maximum kinetic energy. With what? With maximum kinetic energy. So the kinetic energy maximum. You see? Actually, here we have range of kinetic energy, but here we are studying the maximum kinetic energy, the electrons with maximum kinetic energy. And at the same time, this electron undergoes a resistive voltage or resistive work, electric potential energy, or electric work from the other side. How that happens? Because you have negative, and here on the other side you have negative plate repelling it. You see? So negative with negative, you have repulsion. How we can explain that in details? You know, between positive pole and negative pole, you have electric field. Okay? And if you have electric field and you put negatively charged body, like electron, the electric force will be on it opposite to the electric field, as we took this before. So F and E, they have opposite directions because the charge is negative. So as you see now, as a result, this electron, which is between the two plates, So the electron, as you see, which is between the two electrodes, there are two works done on it. The work which is due to the maximum kinetic energy, which is forward kinetic energy maximum, okay? And another work try to stop it due to the electric field and due to the repulsive force, which we can represent it by W or by E. You see? So if the kinetic energy is greater than this resistive electric work, Is it clear? At that time, the electron will continue its flowing and go to the other side. You understand? So if we have ammeter here, like what's shown in the figure, so I read current in the ammeter. I read a value for this current. You see? So if the electron can continue and the kinetic energy is greater than this resistive electric work, is it clear? So the electron, which is moving with maximum kinetic energy, will continue and traverse the circuit and read the current. So this resistive work, let me remember, it's equal to Q times V, right? It's Q times V. It's the electric potential energy, if you remember. Where this Q is E because we are talking about electrons. So the magnitude of this charge is E times the voltage. So as we see, to control this W, we need, because E is constant, we need to control V. Our aim from this experiment is to determine this kinetic energy, the maximum kinetic energy. So to know the maximum kinetic energy, we can measure it when we know the resistive work, because when they are equal, I can get the maximum kinetic energy. Okay, understand me more. So to stop this electron, we need to have, to stop this electron, or the electron stops, sorry. So this electron will stop. So the electron, which moves with maximum kinetic energy, stops when these two works, they are equal and opposite. So when the W is equal to kinetic energy maximum, so they will balance each other. So at that moment we can write EV stopping, because this voltage needs to stop, okay, equal to half mv squared. So when we consider that the voltage used can stop this potential, when it's equal, when the work done, the electric work done is equal to, due to the electric field, it's equal to the maximum kinetic energy. So what we were doing before, we were trying, because initially when we use low voltage, this work is still less than the kinetic energy maximum. Get my idea? So what I need to do, I need to increase the resistive work in order to make it equal to kinetic energy. How to increase the resistive work? By increasing the voltage. So at the instant we get voltage gives me 0 reading on the ammeter, that means this voltage will be equal to the stopping potential. Okay. So as a conclusion, we need to write a conclusion here which summarizes everything we discussed together. So as a conclusion, very important conclusion, that the voltage equal V stopping when the current in the circuit becomes 0. So the voltage, we are adjusting it, becomes equal to V stopping when I read by the ammeter gives me 0. At this moment, I can say that the resistive work, electric work, equal to whom? To the maximum kinetic energy. So when the resistive work equal to maximum kinetic energy, when the current stop moving and the ammeter reads 0, so at this moment I can say EV stopping equal to half mv squared, this mass for electron, this is the maximum speed of electron, and this is the voltage stopping potential. It's what? It's the stopping potential. And we can, if we need to make V stopping subject, so the form of the formula will be Vs equal mv squared over 2e. So this is the final form of V stopping. Is it okay? To understand stopping potential more, let me observe a simulation. Using this simulation, we can understand the idea of stopping potential more. Let me see together. Here in front of us, I'm using ultraviolet because I'm looking for high energy photon. Okay, and the voltage of the battery, you see it's 8 volt. What we observe here, okay, let me start activating it. You see, initially, the intensity is 0. I need to have a certain intensity. Let me start with intensity, for example, like 50%, okay, approximately 52%. Okay, so as you see, we have photoelectric emission. Okay, I'm using here sodium metal. Let me try to increase the intensity a little bit and decrease the voltage. Something happens here. Something wrong. So again, we continue. Sorry, there was a little mistake. I'm adjusting the mistake. Now again, we see ultraviolet. I'm using ultraviolet photons. You see they are emitting normally, so we have normal photoelectric emission. But as we see here, still we are lighting on the negative electrode. I need to determine or to find the stopping potential. So I need to reverse the poles of the battery. So I keep the voltage negative now. It's 0 now. It's negative. You see? So I'm lighting on the positive electrode, which is the anode. And the electrons still going, you see? They are not moving. This voltage minus 0.6 down is not enough to stop these electrons. Because if you look at the ammeter, still I read current. So what I need to do, I need to increase the voltage more. Don't look at negative, look at the value of the voltage. It's 0.6. I need to increase it more in order to let the electron stop and the current here becomes 0. Just let me decrease step by step a little bit. This is minus 1.2, still I read current. You see some electrons in the figure moving back, these weak electron. But the rest electrons, the one with maximum kinetic energy, still moving. Still, I mean, reaching the cathode and traverses the circuit. Let we increase the current more, the voltage more. It's 1.5 minus 1.5, it's 9. Minus 1.6, still I read current, you see? So I need to stop the current completely, to stop these electrons. You see the electrons, they are moving back. Some of them returning back, some of them still reaching the other side. So increase more in the negative side. So it's minus 3.6, and still I read current. Decrease more, I mean increase the negative more. It's the same idea. You see, now the current reads 0. Okay, now the current reads 0. You see they are moving, but they are not reaching the other side. You see, okay, maybe it is minus 4.3. So I adjust it from here. Let me try minus 4.2. 4.2. I read any current? Yes, we have current. So let me try to get exactly the stopping potential. Minus 4.3. Let me try again. It is 0. Let me try minus 4.25. 25. I read current. That means I need a value approximately equal to 4.3 volts in this case to stop completely these electrons. You see? So here, after adjusting the voltage, we realize that the stopping potential is 4.3 volt. If I use sodium method, you see, if I use sodium method and ultraviolet 182 nanometer wavelength, so the stopping potential in this case is how much? Minus, it's 4.3 volt. It's 4.3 volt. You see? Okay. The second step, as we mentioned in the objectives, we need to study the graph of stopping potential versus frequency. To study the graph of stopping potential versus frequency. The aim of studying this graph to know what's the meaning of x-intercept, y-intercept, and the slope. If you remember the previous derivation. So here we have a new derivation identical to the previous, but using the formula of stopping potential. Let me start deriving together to understand or to get x-intercept, y-intercept, and the slope. So we start as before with using the formula of Einstein's equation, kinetic energy maximum equal to E photon minus the work function. Minus what? The work function. So the kinetic energy maximum equal E photon minus the work function. The kinetic energy maximum, instead of kinetic energy maximum, what we put? We put EV stopping, which is the resistive electric work. So we can replace it with EV stopping as we proved it before. It will be equal to E photon. Instead of E photon, we can replace by HF minus the work function. So again, what is the function here is V stopping. What is the variable? Is the frequency. So let we isolate the function, keeping V stopping alone. So divide both sides by E, so HF divided by E minus the work function divided by E. So if we compare this equation, with the equation of straight line, y equal mx plus c, we realize, if we do this comparison, we realize that the slope of this straight line will be equal to h over e, and the y-intercept will be equal to minus the work function divided by e. So that we write this conclusion. So number one, we need to know in this graph that h divided by e equal to the slope. Implies that if we need to determine Planck's constant, we multiply the slope by e. This is very important information. This is number one. Number two, okay. Number two, the minus work function divided by e will be equal to the y-intercept. Implies that, of course, y-intercept, its value will be negative from the graph. So the work function will be equal to minus e times y-intercept. Is it clear? Example, if C equal minus 4 electron volt, then the work function will be equal to minus E times minus 4 electron volt. You see, like this. So the result will be positive. You get the idea, will be what? Positive. The last thing is to know the x-intercept or this frequency. What does this frequency here represent? So number 3, again, EV stopping equal HF minus work function. For x-intercept or at x-intercept, Vs is 0, or here the value is 0. So you will get here HF minus the work function. You see? So V stopping equal to 0, so EV stopping is 0. So HF will be equal to the HF threshold. So again, F equal F threshold, like previous cases, if you remember. So we finished from the derivation now and understanding the graph. Now, after explaining all previous objectives, now we can do some application to understand the previous objectives. Now, let me read together. It's question for 11. Let me read together. One light having frequency. So the frequency of light given is 3 times 10 to the power 15 is shown on a certain metal. Electrons are ejected. So he's telling me we have photoelectric emission. So photoelectric emission occurs. This is very important. So it occurs. Okay. The stopping potential of these electrons is given. So V stopping is given as 7 volt. Asking for the work function. Asking for whom? Of the work function. The thing which relates work function with frequency and V stopping is Einstein's equation. So we start with Einstein's equation, that kinetic energy maximum equal to E photon minus the work function. This is the main formula. Now, instead of kinetic energy, we can replace with the potential energy, or EV stopping. Every time we are working with V stopping, we can replace kinetic energy maximum by EV stopping. Okay. Instead of E photon, I use HF because he gave me frequency, and we're looking for the work function. So I need to make the work function my subject. So the work function is the subject. So the formula becomes equal to HF minus EV stopping. Don't forget that this value gives you joule, this energy in a joule, and EV stopping even here gives me joule, right? If I use SI units. So the final answer will be in what? In it. Okay, now we can substitute the values we have. So equal to 6.63 times 10 to the power minus 34 times the frequency is given as 3 times 10 to the power 15 minus 1.6 times 10 to the power minus 19, which is constant, times the given voltage, which is 7. So the final answer, after doing this calculation, we will get final answer 8.7 times 10 exponent minus 19 joule. This is the final answer of this question. Here we see another application on stopping potential, question number 12. Determine the maximum kinetic energy of electron emitted from zinc surface if they are stopped by a 16 over Newton per Coulomb's uniform electric field. So here to know how to get and to solve this question and giving me the distance. So he's giving me electric field with distance, means don't forget here to understand what I'm doing. You need to know the formula E equal V divided by D. So this formula relates voltage with the given electric field and distance. This is used usually for uniform electric field. And he's asking for kinetic energy maximum. So kinetic energy maximum, to find it, you have many choices. Either to use half mv squared if you have a speed, or you can use Einstein's equation if you have work function and E photon. But you don't have these choices. The only choice to get kinetic energy is to use the idea that kinetic energy maximum equal to EV stopping. You see? So from this concept, to find kinetic energy maximum, you need the stopping voltage, because you can determine it from the given electric field. This is the only choice we can do it to find the maximum kinetic energy. So here to solve this question, we need to do two steps. Initially, we need to find the stopping potential using electric field. So if we say E equal V stopping divided by D, then we can write that Vs equal D times E. So V equal D equal, the distance is in centimeters, we need to change it. It will be 0.03 meters as a unit. And the electric field, it's 16. So the final answer will be 0.48 volts. So this is the stopping potential. Now, I know the stopping potential. So what I do, I can find now the maximum kinetic energy. So kinetic energy maximum will be equal to EV stopping. So it's 1.6 times 10 to the power minus 19 multiplied by 0.48 volts. So the answer will be 7.7 times 10 to the power minus 20 joule. Okay. So this is, so to do this question, as we see, we need to do two main steps. Okay. We continue our students with the question 13. It's the last question on stopping potential. We do it together. Let me read the question together. This question, I think, from the past paper, last year, past papers. So a student uses an experiment to investigate the photoelectric effect as shown in figure A here. The variation of stopping potential against frequency is shown in B. So the graph shows the variation of voltage versus frequency. This is stopping voltage versus frequency, because we are changing the frequency, means we're changing the light, so the stopping will change. On the other side, we see the light is directed toward X, okay, and the other side we have the collector Y. Okay. Let me read the question together. Number one, name the parts in figure A which are labeled X and Y. Name the parts means if they are cathode or anode, where we are lighting on cathode or anode. Okay, we go back to see. If we concentrate well on the figure, we see that X is connected where? To the positive pole of the source or of the battery. You see? Which means this is a positive electrode. And what we mean by positive electrode means anode. So here we are lighting on anode, if you remember. And the second side is connected to negative, so I have what? Cathode. So it's very easy. So X represents the anode or the positive electrode because it's connected to the positive of the battery, and Y represents the cathode. So here, what we do, so part number one, so X represents, we can write the positive electrode. He didn't ask for justification, or anode, and Y represents the negative electrode, which is cathode. Okay. The justification as mentioned before, but here the question's not asking for justification. The part two, what is the stopping potential for photoelectron ejected with, so it's asking for stopping potential, V stopping, when frequency of the light used is 11 times 10 exponent 14. Okay, let me go back to see the figure, because we can just, okay, this is 11, you see, times 10 to the power 14 hertz frequency. So here, if I try to use the figure, if you go to the, okay, this region in the figure is not clear. You see, the value here is not clear. If it's very clear, if he told me what happens at frequency 10, what's the stopping potential at frequency 10? No, sorry, at frequency, for example, here, most of the values not clear. Doesn't give me exact value here. And if it gives me exact value, at that time I say simply I can read the stopping potential from the y-axis because this is Vs. Okay? But if it's not clear at that moment, I need to calculate. So here, don't forget that the x-intercept is f threshold. So he's giving me f threshold. It's equal to 5 times 10 exponent 14 hertz. Is it clear? So we can get and we have the frequency 11, so we can find the stopping potential using Einstein's equation. Okay. So to get stopping potential, and I can get it from the graph directly, so we can use Einstein's equation with the stopping potential, EV stopping equal HF minus HF threshold, because he gave me the frequency and I know the threshold frequency. Even we can simplify this form more. I'm looking for V stopping, so V stopping will be equal. We can take H common factor, F minus F threshold dividing by E. Okay. So V stopping, that we continue calculation. So V stopping equal 6.63 times 10 minus 34 into the given frequency 11. 11 times 10 to the power 14 minus the threshold frequency, which is, I remember it was 5. Let me go back a little bit. Yes, it's 5. So it is 5 times 10 power 14 divided by 1.6 times 10 exponent minus 19. So then we can get the answer. Okay, then we can get the answer. Sorry. So the answer will be 2.48. After doing this calculation on calculator, we will get 2.48 volts. Okay. The last part, which is very important, we need to concentrate more. It's like reasoning question. It requires more concentration. It's between application, okay, and reasoning. How many photons with frequency 7 times 10 to the power 14 are required to emit electrons with total kinetic energy 165? So here the given total kinetic energy, it's not for one electrons, it's for many electrons. So the key to solve this question is to know that the number of electrons or photoelectrons emitted is always equal to the number of the photon used in photoelectric emissions. You get the idea? So every time we need to find the number of photons, if we can find the number of emitted photoelectrons, we can say they are equal. So to know the number of electrons, to know the number of photons they ask for, to find it, okay, if we can find the number of electrons, it's very easy to know the number of photons. So here I prefer to put a plan than to go for calculation. So initially, what we can do as a first step, that we put a plan for our work, then we solve. So first step, we need to know the number of photons, the number of electrons. How to know the number of electrons? Simply, I can find initially the kinetic energy of one electron, and I can do that because I have the given to that. From this kinetic energy, from the total kinetic energy, now we can find the number of electrons by dividing the total kinetic energy by the kinetic energy of one photon. So therefore, finally, we know that the number of photons equal to the number of electrons, so we can get the answer. So to solve this question, we need to do 3 steps. Initially, we find kinetic energy of electron. From that, we divide the total kinetic energy by the energy of one electron to know its numbers. And finally, we can find the numbers of the used photons. Is it clear? So let me continue solving together. So initially, I find, so again, first step, we find the kinetic energy of one photon using Einstein's equation. Kinetic energy equal E photon minus work function. Okay, let me see here. So, which is equal to HF minus HF threshold, or H into F minus F threshold, which is equal 6.63 times 10 minus 34 exponent minus 34. Here 7 times 10 to the power 14 minus 5 times 10 to the power 14. Okay, so the answer will be, so after using calculator, we will get here the kinetic energy of one electron. It will be equal 1.326 times 10 to the power minus 19 joule. So this is the kinetic energy of one electron. One what? Electron. This is very important. So second step, if I know the total kinetic energy of many electrons and the kinetic energy of one electron, I can get the number of these emitted photoelectrons, which will be equal to the total given kinetic energy by the kinetic energy of one electron. Of what? Of one electron. So the answer will be, but be careful, he gave me the total energy in electron volt and the kinetic energy is in joules, so I need to have same unit. So the total kinetic energy is given as 165 times 10 to the power 3 electron volt. Because that, I need to change it to joule, so times 1.6 times 10 to the power minus 19, now it's in joule. And the kinetic energy of one electron is 1.326 times 10 to the power minus 19 joule. So the number of the emitted electrons will be equal 2 times 10 exponent 5 or power 5 electrons. Therefore, that the number of the used photons will be equal to the number of the emitted photoelectrons, so which will be 2 times 10 to the power 5 electrons. And that's all. Thank you very much. Assalamu alaikum.